In this video, I want to talk to you about ways of describing data numerically. We've looked at graphing data in a prior video. Now I want to talk about numbers that describe numbers, numerical descriptions of data. And there are three general classifications that we want to consider. The first of these are measures of center. And measures of center are probably pretty familiar to you. You might remember them from a first statistics class, or maybe you saw them somewhere else, but they are the ones that you probably remember: mean, median, and mode. And what we call them, or which one we use, is going to be determined by what it is we're trying to find out. The mean of a data set is referred to as the arithmetic average, and there's two symbols that you're going to have to get comfortable with. The Greek letter mu is a population mean, and the symbol x with a line over it, and I'll read that as x bar, is a sample mean. So mu is a population mean, that's a parameter, a term we've seen before, and x bar is a sample mean, and that would be considered a statistic, a numerical description of a sample. There's one other symbol I'll throw at you right now that ties in with these three, and I need to talk about it at some point. It's a symbol x. We have three symbols: x, x bar, and mu. X is an individual value. So if we were working with, say, student GPAs, the average GPA of all students is mu. If you take a sample or a subset, the average in that sample is x bar. And when you ask individual students to provide their GPA, that would be their x value. So if you tell me your GPA is 3.2, that's your value of x. If another student says 2.9, that's their value of x. And those x's are combined to form an x bar. And so it kind of works this way. The x's are combined to form an x bar, and then we use the x bar later on to estimate mu. So anyway, I thought I'd give you that symbol now. Mu and x bar are the symbols you need for measures of center. The median is the middle of the ordered data. Not a lot of symbols for median. I'll use the symbol M for a sample. It's a terrible M. Just as an overall statement, you'll probably hear this more than once or twice, but when I'm drawing on these slides, I'm doing it with a mouse. And so sometimes it comes out looking okay. Sometimes it looks like I'm drawing with a mouse. Anyway, median is the middle of the ordered data. If you have an odd number of observations and you order them from small to large or large to small, there's a single value left in the middle. That's called the median. If you have an even number of observations, there's two values left in the middle, and you would take the average of those, and we'd call that the median. Those are the two that you might remember the most. The mode is the one that occurs most frequent in the data set, or most frequently, I guess, in the data set. You can have a bimodal, a trimodal, if there are two or three values occur the same number of times and they're the most. By and large, we don't use the mode very often. It's the mean and the median. But the question that we need to ask is, which measures best? And one way of answering this question, of course, is, well, if you want the average, the mean would be best. If you want the middle, median. If you want the most, the one that occurs most often, the mode. But in general, people are pretty much just asking, hey, what number typifies the center of the distribution? So they don't have kind of a leaning towards the average or the middle or the most. And so they're just asking you, what do you think is the center? And the way I want you to answer this question is, it depends. It depends on the shape of the distribution. So let's go to the next slide, and I have a couple different shapes I want to talk about. I want to talk about symmetric data, and I'll draw a picture for that, and just so I get my spacing right before I start drawing, and skewed. These are the typical distributions that we run into in business data, either symmetric or skewed. A symmetric distribution, as you might imagine, has symmetry. How about that? What a great name. The two sides are mirror images of one another, so that's not a bad looking distribution right there. Somewhere here in the center is where you're going to find the mean, the median. So I'll use M for the median. You're going to find the mean. I'll use mu for the mean. And it's also where you would find the mode. All three measures tend to get stuck in the same spot, in the middle of the symmetric curve. Now let me talk a little bit about how I find those values. The mode occurs the most frequent, so let me put in mode here also. We'll just talk about it pretty quickly here. The mode is going to be the observation that occurs most often. And so we're going to kind of go to the peak. So find the top or the peak of the distribution here, and I'm close to it at least. That's going to be the mode. The median is going to be the value where the area, because area represents the number of occurrences, is equal on either side. And so the median in a symmetric distribution is going to be right here in the middle. The mean is the toughest one to try to figure out. The mean is going to occur where the distribution or the data set balances. So think, if you will, if we could take this normal curve or this symmetric curve off of the screen. If I could put my finger right here in the middle, because it's symmetric, that's where it would balance. If I tried putting my finger over here, well, there's way too much weight on the left-hand side. It would fall over. Likewise, if I was over on this way, it wouldn't balance. And so a good way of trying to figure out the mean is where would it balance? And so that's the idea that you'd get with a symmetric curve. The mean, the median, and the mode all appear in the same spot. So it looks like it won't matter that much. Okay, let's talk about skewed distribution. So I'm going to draw a nice skewed right distribution. Okay, let's even extend it out a little further. So most of your data falls here. In fact, the mode, the one that occurs most often, I'm going to go to the peak there. There's the mode. And then obviously there's a lot more area to the right of that than to the left. So if I want to try to even out the areas, the median's going to have to be over here. And so I'll give that the M. Well, that's a terrible M. You get the idea. The median is right here, but that's not going to be the balance point. What happens in skewed distributions, these really big observations out in the tail out here, the big X's that you see, the biggest observations, they tend to pull the mean towards them because the mean looks at every single observation. And so the mean in this case would get shifted far away. And what I'll say now is that the mean chases the tail. Okay, this is called a skewed right. It's skewed in the direction of the long tail. It's a skewed right distribution. And the mean is influenced by these really big values out here in the tail, and it goes towards them. The median really is only looking at the middle one or two observations, so it's not influenced by those values at all. And so what we tend to say is that in skewed data, the median is considered the best measure of center. We like the median if we know we have skewed data. In symmetric data, if you kind of followed along with what I said, it really doesn't seem to matter, but it turns out it does. We're going to use the mean in symmetric data. Now, Y has to do with how accurate these measures are. Sure, they give us values that are about the same, but the mean is going to be the most accurate. And we can talk a little bit more about that when we talk about sampling distributions in a little bit later on in the course. Not too much later in the 6-week course, but a little bit later. We'll get to some ideas talking about sampling distributions, and it turns out the mean's the best one to use. So it's the mean or the median. The shape kind of dictates which one we use. Now, I have this conversation every semester with students, and it looks like, gosh, we're going to be using both these things. Turns out, a lot of what we do in statistics, that's a terrible looking asterisk, a lot of what we do in statistics ends up with symmetric data. And so we're going to spend a lot of time talking about means and not so much time talking about medians. You might remember normal curves. You might remember t-distributions. Those are both symmetric curves, and so we work with the mean, we work with the sampling distribution of the mean, we work with population means, and so that's what we're going to be working with this semester. So those are your measures of center. You got the mean, the median, and the mode. The median has its usages, but it's primarily the mean that we spend time with. The second measure that we want to take a look at, the second type of measure, I guess, are measures of variation. We can have two distributions, draw a quick little picture up here, that are centered at the same spot that look very different. Distribution A here is much less spread out than distribution B. And so we talk about measures of variation or measures of dispersion. That's another name for it. And we have 3 measures of variation as well. And you can see these in your notes. I didn't even give you space to write these in. The variance, which has a snazzy little formula, and this should be, by the way, n-1. Don't know why it got left off the notes, but it did. The variance has a formula, and if you spend any time in your Stat 1 classes calculating these formulas, I'm going to apologize for that every single time because I don't want you doing these calculations. But if you look at it, the variance takes a look at the symbols here, x minus x bars. Taking a look, how far do the individual observations, remember that's what we said the x's are, how far do they fall from the mean? And this is a symbol for a sample mean, sample variance. A population variance actually looks something like this, and I think we see that in the formula a little bit later, or a graph that I draw, sigma squared. So the standard deviation is square root of the variance. S is going to be the square root of s squared. That's a sample variance. The sample standard deviation, and that's actually the one we see in the plot, is sigma. So those are some symbols that you'll see used. And you're going to have to get comfortable with the symbols because we will see those. You do not need to get comfortable with the formulas. A lot of my former students take me in this class, and they'll, if you get a chance to talk to them, and I know it's difficult because obviously this is a online class that you're watching right now, but if you had a chance to speak to them, they say Mark would give us the formulas and show us the formulas, and in this case, seeing that it's taken a look at how far observations fall from means, that's kind of the way that we measure our variation. I'll show you the formulas, but I'm not going to ask you to use them. The computer will do this for us, and you need to be able to tell me what these things mean. So the variance and the standard deviation are kind of a team. And typically I say the variance is the formula part, the standard deviation is the interpretation part, but I'll get that in a minute. And then the last one, the last measure of variation is called the range. And the range is the difference between the largest and the smallest observations. Obviously, more spread out the data is, the better the chance that the range is going to be greater. Much like the mode, it's easy to calculate. Much like the mode, we don't use it for very much. And so it's a standard deviation. And so you see here in the notes, I say which measure is best? Standard deviation is best. That's the one we're going to work with. And again, I'm not going to ask you to do the calculations, but I am going to be interested in you being able to interpret the standard deviation. And so we do that using a couple of different rules. You may or may not remember these two rules. Chebyshev works for any data. Any data set you get, it's going to work. The empirical rule, symmetric data. Generally, we talk about mound-shaped symmetric. It becomes a normal curve later on when you're in a Stat 1 class. Those are the two that typically most Stat 1 classes teach, depending where you had Stat 2, or excuse me, Stat 1. You may have looked at the modified empirical rule, and I'll say for this one, skewed data. A lot of times in business and settings, we run into symmetric data. Okay, empirical rule is good for that. And we also run into skewed data. Well, if you only have these two, and I say you have a skewed data set, you're going to use Chebyshev. You're going to be forced to, because if those are the only two choices you have, Chebyshev's the way to go. The modified empirical rule works when you're working with skewed data, and as we're going to see, it has some nice properties. So typically we're using one of these guys. And really what I'm trying to do here when we're interpreting descriptive measures, we're trying to interpret the standard deviation. I'm trying to give you a way to get some useful information from a standard deviation. And so let's jump into Chebyshev and see what Chebyshev says. Now let me go ahead and put these up. I know these aren't in your notes. So you're going to want to copy them. And you can see that I use the sigma here. That's the standard deviation. Mu is a population mean. I could replace this with x bar plus or minus 1s if I was using sample symbols, but I chose to use population symbols. Chebyshev says, remember, it works for any data set. It says at least none of the data fall within one standard deviation of the mean. Not helpful at all. At least none of it, at least 0%. Chebyshev says at least 75%. Pretty big jump there, right? From 0 to 75, at least. Probably more. That's a phrase that kind of goes along with Chebyshev. At least 75% of the data fall within one standard deviation of the mean. That's pretty good. Chunk of your data. What we're looking for with this, the way that we want to interpret the standard deviation is we want to say where does most of the data fall? And our definition of most goes back to a prior lecture where we talked about reliability. And in that lecture we said we want our reliability levels to be in the 90 to 99% range. So while at least 75% is a lot, it's not most. Most for us, if we're using Chebyshev, is right here. At least 89%, probably more, gets us to where most. So we'll interpret the standard deviation to say we expect most of the data, when we're using Chebyshev's theorem, most of the data, and the data, we're talking about the x's here, the individual observations, most of the GPAs of students will fall within 3 standard deviations of the mean. Now the difficult math, the calculation of the mean, the calculation of the standard deviation, we're going to get those values on printouts, but you're going to have to do a little bit of light math. You're going to have to take that mean and add and subtract 3 standard deviations. It's usually not real difficult. I know I run into students all the time who say, oh, I'm not real good at math. I don't know if I'm going to do well in statistics. Well, my response to that is you don't need to be good at math. Look at this math right here. Can you multiply by 3? Can you add and subtract? Because that's the extent of it here. Later on, we're going to be dividing, but basic math is all you need. We're going to let the computer do the more difficult math for us. And so if you're forced to use Chebyshev, if you don't have a better rule to use, then we'd say most things fall within 3 standard deviations of the mean. Now, to give you some insight as to why the numbers change, because I'm going to move to the empirical rule now, and you're going to see the numbers get a lot better, I'm going to equate it to something else. A lot of you guys are probably taking this class in Florida. That's where I'm based. I'm based out of Tampa. But who knows? It's an online class. We could have people from all over the place that are registered to take it. But in Tampa, in the summertime at least, our weather pattern is pretty easy to figure out. Our weather is hot and it's humid, and the number I want to talk about here is the chance of afternoon rain stays pretty consistent, and I'll just throw a number out. It's usually in the 30 to 40%. Let's say it's a 40% chance of afternoon thunderstorms. Okay, now I'm filming this. It is June 1st when I'm filming this, and there's about a 40% chance of rain. Now, if I go to July 1st, okay, so if I move fast forward a month from now, the chance of afternoon rain probably is going to be 40%. August 1st, September 1st, even October 1st, pretty much in the Tampa area, our weather stays pretty consistent. The chance of afternoon thunderstorms is 40%. And I know you're thinking, where the heck is he going with this? All right, here's where I'm going with it. Suppose you were sitting in a classroom, okay? I know you're online, but suppose another class, you're sitting in a classroom. It's summertime, you're in Tampa, and you know there's a 40% chance of rain, but you've been sitting in the classroom for a couple hours now, and you hear some noise. It sounds like thunder. And maybe the lights flicker, like it's lightning out there, and the lights are flickering on and off a little bit. And then all of a sudden, someone comes into the room late, and they are drenched. They're just soaking wet from head to toe. Okay? Now, if I'm standing in the front of the classroom and I see this happening, and I ask this question, hey, what do you think the chance of it raining right now is? Now, we haven't been outside, and think about being in a classroom that's got no windows, so you can't actually see outside. One of the classes I typically teach in is like that. And I asked the question, what do you think the chance of it raining right now? Well, typically you would say 40%, but wait a second, didn't we have some clues, some kind of context clues? We heard some thunder. We saw the lights kind of flash on and off, maybe like a lightning strike. And we just saw someone walk into the classroom that was soaking wet from head to toe. I think it would be smart if that was the case that you would say, well, I think it's a lot higher than 40%. In fact, I'd probably go out on a limb and say it's 100% because all the clues are pointing in that direction. Make sense? And of course, you should be thinking, yeah, that's perfectly logical. Well, here's the argument I want to make with you, or here's the discussion I want to have with you. Let me go to the next slide. When we talk about the empirical rule, someone tells me we're working with a mound-shaped symmetric distribution. We're working with a curve like this. Now, Chebyshev just got done saying that at least 0% of the data fall within one standard deviation of the mean. Now, if I know the empirical rule, if I know that I'm working with the empirical rule and we're working with this kind of shape, I know that there's a big chunk of data that falls really close to the mean. I know that this is going to be a lot more than at least 0%, and that's reflected in the numbers. The empirical rule, by the fact that we're using it, we know the shape. We know that the data is bunched up around the mean. And so what we notice is the empirical rule numbers are better, that at least 0, that at least 75, that at least 89 that we just saw with Chebyshev's theorem. Look at the numbers now, approximately 68. That's a lot. It's not most, but it's a lot. Look at the next number. Yeah, that gets the asterisk right now. That's most. That's where most of our data falls. So if we know that we have a mound-shaped symmetric distribution, some would call it a normal curve, bell-shaped curve, lots of names for it, what we're going to say is we expect most of the data to fall within 2 standard deviations. We're going to be more accurate. With Chebyshev, we go out to 3. We have to in order to get our 90 to 99%, our big reliability, our big percentage. But with the empirical rule, we can chop it down to 2 standard deviations. And so that's how we're going to interpret a standard deviation. Again, the mean, the standard deviation are going to be done for us. That math's going to be calculated by the software. You're going to have to do some adding and subtracting, except this time you're multiplying by 2 instead of 3. The empirical rule goes on to say almost all of it's going to fall within 3, but we're looking for most. And most for us is going to be in the 90 to 99 range, 99% range. That one's perfect. And again, some people just look at Chebyshev and the empirical rule and they say if you're working with skewed data, sorry, you got to use the empirical, or I'm sorry, you got to use Chebyshev. That's why I want to, this semester, if you haven't seen it before, I want to give you the modified empirical rule. And again, it works for skewed data. So again, most of the data is going to be found around the mean, and you can see the numbers reflect that. I'm not sure why these are underlined, but they are. You don't need to underline them. 60 to 90% fall within 1 standard deviation. Not real accurate, but the way a skewness occurs, it can be a little bit of skewness, it can be a lot of bit of skewness, so 60 to 90%. The more skewness, the higher the number actually is. The more skewed the data become, the bigger the standard deviation is. And so you end up with a larger percentage closer to the mean relative to the standard deviation. But here's where we're going to go with this. Here's our most again. 2 standard deviations. And again, approximately 100% fall within 3. And so the moral of this story, and you can see this in your notes, is that most data fall within 2 standard deviations of the mean for symmetric and skewed data sets. So even when there's skewness, now if you're only given the 2 choices between Chebyshev and the empirical rule, I couldn't really make this statement, but the fact now that we're talking about the modified empirical rule, I can. For most data sets, most of our business data sets are going to be symmetric or have some skewness. We're going to be able to use 2 standard deviations. So you're going to have to do this math. In fact, that's how I'm going to have you interpret a standard deviation. I want you to tell me that the interpretation of the standard deviation is most of your data, most of your X's in the data set. Most of the students are going to have GPAs that fall within 2 standard deviations of the mean. So a little bit of math and you can tell me what the minimum value is going to be, what the maximum value is going to be for most of the data. So it's a pretty handy little tool. That standard deviation interpretation is one that we get a lot of mileage out of. We use that for a lot of different things. We'll see that several different times throughout the semester. All right, so that's our interpretation of a standard deviation. So we've had measures of center, the mean, the median, probably not the mode. We've had our measures of variation, and that's really just a standard deviation. And I want to talk about one more. I want to talk about measures of relative standing. And there are 2 main measures to look at. The one that everyone probably is familiar with is percentiles. And the key word is the percentage below. And I'll give you an example. The lower quartile, lower 25th percentile, 25% of the observations fall below. The 75th percentile is called the upper quartile. 75% of the observations fall below. There's also something called the middle quartile, where 50% of the data fall below, but we call that the median. So we had another name for that. The 60th percentile, 60% fall below. And you can always look at the flip side too. If 60% fall below, 40% fall above. The lower quartile is 75% above. The upper quartile is 25% above. So the percent below, the percent above always sum to 100%. So that's how percentiles work, pretty straightforward. Honestly, though, we don't use percentiles all that much. What we're going to use more than that are things called z-scores. And you can see, I'll give you you probably already have it in your notes, but you can see that I have a couple formulas here already spelled out for you. The z-score formula, and look at the symbols here. X is an individual value, mu is a mean, and because I'm using mu, it's a population mean, and I'm using sigma, it's a population standard deviation. It says take an individual value, subtract the mean, divide by the standard deviation. This does the same thing, it just uses sample symbols. This is the formula on the right-hand side here that we typically use. But to find a z-score, we take your value, or an individual value, it doesn't have to be yours, an individual value, subtract the mean, divide by the standard deviation. And the z-score will tell us how many standard deviations an observation falls from the mean. And so that's not it. You see there's another piece there, but I'll try to emphasize why that's important. If I tell you after you take your midterm exam that you fall 2 standard deviations away from the mean, that's not enough information, because if you fall 2 standard deviations away from the mean, that could be one of 2 directions. It could be above the mean, in which case, wow, good job. You're doing great in this class. Or it could be below the mean, in which case I'm not going to say good job. I'm going to say, let's talk about the drop dead line. Let's see what we can do to do things better. It's a completely different conversation. And so not only do we need to know how many standard deviations, but we need to know which direction as well. Above the mean are positive z-scores, below the mean are negative z-scores, and we need both. Okay, so we have measures of relative standing, and for our purposes, the z-scores here are the one we use more often. We don't do a whole lot with percentiles. We don't see z-scores a whole lot, but they're in the background of a lot of things we do. Now, one place we will see z-scores is with outliers. And we're going to define outliers to be outliers that are observations that fall outside where we expect. Where do the expectations come from? Our rules. If we have symmetric or skewed data, we expect things to fall within 2 standard deviations. If we don't have either of those data sets and we're forced to use Chebyshev, we bump it out to within 3. And so the outliers are the observations that are out there. Okay? Now there's 2 methods for detecting outliers. If what I've talked about in this video makes sense to you. Okay, it makes sense to me, but that doesn't mean it makes sense to you. If it makes sense to you, the z-score method should be pretty straightforward. We talked about what's expected. We said depending on the shape, it's either within 2 or within 3 standard deviations. So anything that falls outside of those values, we're going to say those are outliers. The z-score gives me a number that tells me how many standard deviations an observation falls from the mean. And the sign, positive or negative, tells me if it's above or below the mean. So let's say, just for argument's sake, that I have a z-score that's 4.2, positive 4.2. What that's telling me is that observation falls 4.2 standard deviations above the mean. My question is that an outlier? Again, if you followed along with what I've talked about in this video, you're going to say, yeah, it is. How do we know that? Because it falls more than 4 standard deviations away. Anything outside of 3 standard deviations is an outlier, regardless of which rule we're using. If it's -5, that's an outlier as well. How about if it's a 1.2, positive 1.2, negative 1.2? Can you use them interchangeably here? Is that an outlier? That observation falls 1.2 standard deviations above if it's positive, below if it's negative. They're not outliers. None of our rules say 1.2 standard deviations away from the mean is unexpected. And so what you start to see is that if the z-score is between plus and minus 2, it's not an outlier. If it's outside of plus or minus 3, it is an outlier. The only time you have to be a little careful, what if your z-score is, say, 2.5? Or let's say it's a negative 2.5. That observation falls 2.5 standard deviations below, that's what the negative signs tell me, below the mean. Is that an outlier? That depends. That depends on the shape of the distribution, doesn't it? Because if we're using the empirical rule or the modified empirical rule, that value is not expected. We expect things to fall within 2, plus and minus 2, within 2 standard deviations of the mean. If we're using Chebyshev, then this negative 2.5 would not be considered an outlier. So if we're using Chebyshev, that's not an outlier. If we're using the empirical or the modified empirical rule, it is. Does that make sense? Hopefully that makes sense to you. Okay, if you followed along what we talked about, our expectations are based on the shape. The shape dictates the rules. That's where our expectations come from. The z-score is just saying, oh, this observation falls here, and now we're just comparing to that. So that one's pretty straightforward. The one that's a little new is the box plot method. Now the box plot, I'm going to show you an example on the next page, but let me just talk to you about it. It doesn't work with the mean and the standard deviation. Obviously the z-score does. It works with, remember, x minus x bar or mu divided by the standard deviation. So I'm either going to use an s or a sigma. That's an s, not a 5. My s's and 5s sometimes look alike, especially when I'm drawing with a mouse. So that's the z-score. The z-score relies on the mean and the standard deviation in the calculations. This guy, the box plot, is based off of the quartiles. And I'll show you what I mean in the next frame, but let me spell it out here. It's based on the quartiles. So it's a different way of identifying outliers. One of the things we like about the box plot is there's a graph. It's a graph, another graphical display. So we looked at stem and leaf displays. We looked at bar graphs. We looked at pie charts, scatter plots. Here's another one for you, a box plot. And what you'll look at, it's obviously a box. At the lower edge of this box right here, that's the 25th percentile. That's the lower quartile. At the upper edge, which is, I'm having trouble, there we go. At this edge right here, that's called the upper quartile. Now the difference between these things is referred to as the interquartile range. Some terminology that you'll never need to know again, but that's what it's called. The difference between the quartiles is called the interquartile range. And this guy right here, if these are the lower and the upper quartile, this is going to be the median, the 50th percentile. And you're going to see where that's located at in the box as well. So 25% of your observations fall below the lower quartile. 75% fall below the upper quartile. So half your data is in this box right here. They're not outliers, but that's where half your data is going to be located at. In fact, the observations that fall just around the edge of the box, those aren't outliers either. What the box plot's going to do, it's going to take a look at this distance, this inner quartile range I talked about, and it's going to go 1.5 of those. And you don't see it drawn in the picture, but it's called an inner fence. And anything that falls outside there, in this case we see an asterisk, these are called suspect outliers. That's a U. It's a terrible U. Suspect outliers. That's what the asterisk is going to refer to. And then you can find other box plots that go another 1.5 quartiles, or I'm sorry, inner quartile ranges, and there's another fence, and then there's another symbol that we don't see on this plot because we didn't have any, but that symbol is going to be an O, and those are going to be outliers. When you guys actually generate some of these things for me, you might see the other symbol, and those are outliers. Sometimes they're called highly suspect outliers. So you have outliers and suspects. I don't use the highly suspect, but we'll just call them outliers. And so the asterisk refers to the suspect. The O refers to the outlier. Different software packages use different symbols, but that's what we're going to see this semester. Now, the data set that I pulled here that I'm working with is I asked students, how many hours do you exercise per week? And it looks like this number is around 3. This number looks to be, what is that, going to be about 10-ish? And so somewhere out here in the 20, 21 range, somewhere in there is where I would probably get this inner fence. This is going to be, what if I had a student who said they exercise 40 hours per week? Well, they're going to be far enough out there that that would be listed as an outlier. So hopefully when you generate some of these on your data sets, you'll see some different symbols. But the box plot is another way of identifying the unexpected. We call them outliers. And so to recap this video, we talked about measures of center, measures of spread, ways of interpreting standard deviations. We talked about measures of relative standing. Z-score is the one that was real important. We identified those observations that are out there as outliers, the ones that fall pretty far away. Remember earlier I said in skewed distributions, the mean chases the tail. The other way of saying it is the mean chases the outliers. It's very much influenced by the outliers. So when you're looking at measures of center, when you have skewed data, you don't want the observations to have an effect on your measure of center, and they affect the mean. And so that's why we like the median over the mean, just to kind of put some things together for you. Take a look at the homework problems associated with this material. Make sure that all sounds good to you. And then check out the competency checks to make sure the main ideas are sticking with you. Nice thing about online lectures, this is going to be around forever, or at least through the end of the semester, which is forever enough for you guys. If you have any questions, you can always jump on the discussion board and you can post a question. Until next time, so long.